Hi everyone, and welcome to the second lesson of the second module. Here we're going to talk about what the gradient descent is. So, starting from the definition, it's an algorithm, it's used for optimization, used iteratively, and with each iteration it tries to adjust, to minimize the cost function by adjusting its parameters. How it looks in reality, so we have parameters theta, and by each iteration we do the same thing with all the parameters. So we say theta j equals theta j minus learning rate, some value. It's usually 0.01, as you remember, and a partial derivative from the theta j from the j from theta function. We're gonna talk a bit later about what is a learning rate and why we use this thing. So what do we do? I first say that what the gradient is just a vector of the derivatives of the differentiable function. And here's the main slide. Here is the most important and interesting from my perspective part. What is it created for? So we have this thing again, theta equals what it's vectorized right now. Theta equals theta minus learning rate multiplied by gradient from theta, from j theta. Let's say we have theta from two functions, or j from two functions, theta 0 and theta 1. Alright, so we have some sort of a cost function. Let's say it's function, obviously, and we can plot it. It's as a graph, as a 3D graph, because we have two parameters here. So here's the first one, here's the second one, and here is the value of the function. And if we graph it, if we plot it, it looks like that. And when we're high, we see a huge value of the cost function, and obviously we want to minimize it. And what we do here, let's say here is theta 0, 1 and theta 1, 1. We adjust both values based on the learning rate multiplied by their importance. Here is an important part, because why don't we just take the value? Because if we took the value, we would go to a straight line. We would not adjust each of the coefficients based on how they affect the cost function. So this derivative means that if the fastest way to get to the bottom is to go not with, for example, 0.1 and 0.1 for both thetas, but 0.1 and 0.05 for theta 1 and for theta 0 and theta 1, correspondingly would probably say that the gradient from theta 1 is lower than the gradient of theta 0, and so here's why we use the gradient. And with one step we would go here, 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 and until we are in the local or the global minimum. And what is the learning rate? How to say that? Without learning rate, it would like intuitively, it would give us the direction, the steepest direction of where we should go. But the learning rate says how far should we go in this direction. So imagine the learning rate would be 500, where here is from 1 to 0. We would need to go from this point to this point. But with learning rate 100, not 100, but let's say like 1, we would probably go something like here. So to this point. And on the first glance, it looks just great, because we would go faster. But then we will go here. And obviously in this point we need to get back. We got here, 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 here. And we would not get under any chance, under any circumstance, to this local minimum. Or let's say the learning rate is 0.00001. We would probably get here, 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 and it would be really slow. So the golden value is 0.01, and just use it like that. So now you understand the Bayes gradient descent, and why it's called this Bayes, not just gradient descent. It's just is that because it adjusts all of the, you see vectors, it adjusts all of the algorithms, all of the parameters at once with one iteration. And gradient descent is used not only in linear regression but in loads of functions because it's intuitive and it can use for anything, because we have a cost function in we have the cost function in almost every model, and we can use gradient descent. So that's it. So thanks for watching.